Hello, hello, Chem 20. We are into week 10 of distance learning, and this is the second last week that you'll have new material, which means next week, week 11, will be your last week of new stuff for Chem 20, which is kind of crazy that we have officially gotten this far. The final 12th week then is going to be a review assignment, which will encompass the entire course. So please be prepared for that. Although there will be nothing new to learn, it will still be something you're definitely going to be having to look back at old material. It is not an exam per se, but it is definitely cumulative. So, speaking of which though, let's move on. Now, we're going to be focusing on two main concepts this week: limiting and excess reagents, with builds right into the stoichiometric process that we've already been doing, and then percent yield, which of course builds onto stoichiometry and limiting and excess reagents as well. The last point there is more of a lab activity. Well, you'll be watching a lab online go through a step-by-step process, and you'll have to do an analysis on the investigation. Now, before you start watching this podcast, if you have not yet linked to the video that is in the PDF form of your notes, please do so. There's a little 5-minute YouTube video on limiting and excess reagents that I would like you to watch first. So pause this, go watch that, and then come on back so that we can start to go through together limiting and excess reagents. Okay. All right, guys, if you'd been in class right now, we would have made some s'mores. And unfortunately, we can't do that, but I want you to still visualize what would be happening here. Now, essentially, we would have a scenario where you're going to take a certain recipe in order to make a good s'more. And the recipe I'm going to use is 2 crackers and 3 pieces of chocolate and 1 marshmallow. This should be an arrow here as an equation, is going to make us 1 s'more. Now, question is then, what if I had 40 crackers, and assume I have as much chocolate as you need and as much marshmallows as you need, but I only have 40 crackers? How many s'mores could you make? Well, ultimately, guys, all we need to do is take the amount that we have and recognize that we need 2 crackers per 1 s'more. So I would go like this. I'd be like, okay, I've got 40 crackers, divide by 2, and 20. Oh, I could make 20 s'mores. Why? Because the crackers decides the number of s'mores. Pretty easy math when you stop and look at it. Now, don't get thrown off by that. Keep in your head that this math is not as hard as you may end up thinking it is, right? Keep things straight in your brain. Well, let's imagine then we go back to the same essential recipe. 2 crackers, 3 chocolates, 1 marshmallow gives us a s'more. What if I have this though? I have a total of 32 crackers. I have 3 chocolate bars, and every single chocolate bar has 24 squares. And I have 1 whole bag that has 44 marshmallows in it. Now the question is, how many s'mores could I make? So to stop and think about this, you essentially need to decide which of these ingredients, the crackers, the chocolate bars, or the marshmallows, are going to limit the amount of s'mores that can officially be made. Okay, let's go through a process. If we'd been in class, I would have asked you to do this on your own and give me the answer to get a s'more, but we'll go through it together here. Similar to when we looked on this side and I said I had 40 crackers, except this time we got 32. 2 crackers per s'more. So 32 divided by 2, this one I get 16. I could make 16 s'mores in that case. Okay, let's look at the chocolate bars. 24 squares of chocolate each, so 24 times 3. I've got 72 chocolate or pieces of chocolate in total. I divide that 72 by 3 and I've got 24. Why 3? Because of the 3 in front of the chocolate. Okay. Marshmallows. I have 44 marshmallows. I need 1 marshmallow per a s'more. So that's 44. Look at where these numbers are coming from. 2 in front of crackers, divide by 2. 3 in front of chocolate, divide by 3. 1 in front of marshmallow, divide by 1. Interesting. Now, what limits it? Well, which is going to get used up first? Which is going to be gone? It's going to be the crackers. So crackers limits it, therefore crackers decides how many s'mores we'll have 16 s'mores total. We have an excess amount of chocolate. We have an excess amount of marshmallows. Unfortunately, it is the crackers that dictate this. Okay, so if I went through that problem and you went, yeah, Sakura, this is no big deal. This isn't so bad. Good. That's what I want, because that's going to let you have in the back of your head to understand these limiting and excess reagents. So ultimately, just like we saw in that recipe, the coefficients are really key, right? The coefficients of that balanced chemical equation. Now, these are stoichiometric coefficients because we use them to use our stoichiometry calculations, right? We've been using these for the last couple weeks. Now, ultimately, if the reactant amounts are perfect and they correspond beautifully to the mole ratios, everything matches, then we have stoichiometric amounts. That's all fine and dandy. Reality is, though, it doesn't exist that often. So ultimately, if every single reactant is completely consumed, that's that definition of stoichiometric amounts. Now, in reality, that's usually not how it goes. Something gets used up first, we have leftovers. This is more typical. Here's another example of food. Food just works well for these things. Now, if I have a total of 5 hot dogs, right, the actual beef part, and I have a total of 4 buns, I'm not going to be able to make 5 hot dogs because I'm going to run out of buns. I'm only going to be able to feed 4 people. So that means that the buns are limiting. What's going to be left over? What are you going to have extra of? You're going to have an extra hot dog, the actual wiener portion, right? So the bun determined the total product, right? Not the hot dog. The hot dog itself, I had in excess. I've got them left over. So ultimately, the amount of product that limits the reactant used up, right? So the products are limited by the reactant used up or totally consumed first. Alrighty, new terminology. This is really important terminology because you're going to have variations of this in the questions. If you're going to make sense of the questions, you ought to know what the words are. So first thing first, you'll see the word limiting reagent and limiting reactant. They mean the same thing. They are whatever reactant is used up. So in other words, whatever one you have in a smaller amount. Now be careful, I'm not saying smaller mass. I'm saying smaller amount. And that gets a little bit more interesting to figure out. Vice versa, any reactant that's left over that you have extra, that's the one that's the excess reagent. This will also be known as an excess reactant. Okay? So keep both of those in the back of your heads. Very important terms, ones that are going to be coming up again and again and again. Now here's something weird, and I have this underlined and highlighted in the notes that's really important and does throw off people. That limiting reagent, the one that's going to run out first, might not be the one with the fewest moles. And I know when you first hear that, that sounds really weird. It's like, well, of course it's the one that's the fewest. Not necessarily. It's going to all depend upon the coefficients. Now, ultimately, the limiting the reactant is the one that will end up producing the lowest number of moles of product. And it's producing the lowest number of moles of product because it runs out first. Okay? This is key. I'll give you an example to show you a little bit more of what I mean. Let's just say we have a reaction where we have A plus 5B produces AB to the little subscript 5. Now, this is the balanced reaction, but what if I say, hey, I've got this amount of A. I have 3 moles of chemical A, and I have this amount of B. I have 4 moles of chemical B. Which one is actually going to run out first? Now, at first glance, the instinct is to be like, oh, this one's going to run out first because there's less of it. Be careful. What is the ratio? And I want you to look at these front numbers. I've got a 5 here and a 1 here. That literally means you need 5 times the moles of B for every 1 mole of A. Why? Because look at what you're forming, right? There's 5 of the B for every 1 A. So that means if I've got 2 moles of A, I need 10 moles of B. If I've got 5 moles of A, I need 25 moles of B. If I've got 1 mole of A, I need 5 moles of B. You get the idea. Ultimately then, the method used to figure this out is we take the number of moles and we say, okay, I'm going to divide by the coefficient and see what I end up with. So 3 divided by the coefficient of 1, well, this is indeed 3 moles, so that's pretty good. Now over here, 4 divided by the coefficient 5, woo, this is 0.8 moles. Guys, this one is actually, from a ratio perspective, going to be less. So that's my limiting reagent. Look at those ratios. If I wanted to react with 3 moles of A, technically I would need a total of 15 moles of B. I don't have even close to that. B is limiting. Let's do another example. What if we've got this reaction? 1.5 moles of hydrogen reacting with 1 mole of oxygen. Well, first things first is write down what you've got. So the number of moles of hydrogen is equal to 1.5 moles. And the amount of oxygen is equal to 1.0 moles. Question then says, what is going to be the limiting reagent? Which means, what is going to run out first? Well, first things first is we need to actually compare these as related to their coefficients. So we take it and go, okay, I'm then going to take my 1.5 moles and I'm going to divide by the coefficient in front there. So in other words, I'm dividing by that 2. Going to do the same thing for the other one. I have 1.0 moles and I'm going to divide by the coefficient here, which is 1. Why is it 1? Well, guys, that should be somewhat obvious, right? There's nothing in the front. It's not 0. No, it's 1. We're just lazy about writing ones mathematically. When you do that, you end up with the hydrogen 0.75 moles and with the oxygen 1.0 moles. Then it's as simple, once you've done that, is look at it and be like, okay, which one's lower? This is the lower number. This is our limiting reagent. Now, since that thing runs out first, guys, that means that it's going to dictate how much product we get. It's going to be all about the hydrogen. Now, here's where people start to make mistakes. Are you reacting 0.75 moles of hydrogen? No, you're reacting 1.5 moles. So that's the one that you need to use in the ratio. Show you what I mean. The ratio here is we're comparing moles of water to the moles of hydrogen gas. Why hydrogen gas? Because it was the limiting reagent. The ratio of those two is 2 moles to 2 moles. Oh, that makes it easy. We have, for this one, X amount of water, we don't know how much, but not 0.75 of hydrogen gas, guys, 1.5 moles of hydrogen gas, right? That's what actual amount is actually reacting. So we need to go with it, okay? Cross multiply and divide. You end up, pretty easy math, let's be honest. X is equal to 1.5 mole of water, H2O liquid, produced. So even though you were given amounts for both reactants, both of them, we don't use the amount given of the oxygen. Why? Because there's more than we need. There is an excess amount. It is the hydrogen that runs out first. So that is the one that is going to dictate the amount of product we actually end up with. Okay, there is a step-by-step process for doing this, which might make it feel a little bit easier, and then we'll do a couple of examples together. So the first step is super logical. It's exactly what you would think. We need, of course, a balanced chemical equation. This always needs to be the case, guys. Nothing new. Now, for this, you'll be given the amount for both reactants. So you got to convert that to moles. And here's the thing. You're going to get N moles for both of them. It might take some calculations, but now it's like, oh, which one do I use? That's where we use those mole ratios. So we're going to use the coefficients, in other words, is what I'm trying to say. Use the coefficients on those reactants to figure out which one is actually limiting. And that's where it is that lowest number, just like we got with the hydrogen gas. Then use the number of moles of the limiting reagent, not of the other ones, not of the other reactants, but specifically the limiting reagent, to actually calculate with the mole ratio what the product is going to be, right? So the actual amount reacted. Use actual amount reacted. That's key. It's an easy mistake to make. It's one you're going to have to watch for. Alrighty. Best way for us to do this is jump on in and put it into practice. So, starting right from the beginning, we've got a certain mass of magnesium put into a certain volume at a concentration of hydrochloric acid. There's our two reactants, magnesium, hydrochloric acid. You've just been given a way to find the number of moles of both of those. So you got to figure out what on earth the limiting reagent is. Then this one has a twist. Ooh, what amount of excess reagent will remain? That gets interesting. What amount won't be reacted? So guys, welcome to an academic course where it's not just cookie cutter questions. You have to think a little. Go figure. Anyway, balanced chemical reaction. Let's start there. We are taking magnesium solid and reacting it with hydrochloric acid. Now, I have a metal reacting with not an ionic compound, but something I can still swap out. This is a single replacement reaction. So the hydrogen gas is going to get kicked out by the magnesium, right? The hydrogen comes out, becomes H2, it's diatomic. Magnesium goes in. We now have magnesium chloride produced. And it'll be aqueous. Why? Because I checked the solubility table, and it is. Balance this thing. There will be a 2 in front of the HCl. Okay, that's step 1, guys. That's all we've done so far. Step 2, let's figure out the amounts of both of these things. So going into step 2, I've been given a mass of magnesium, and in the question it's 1.25 grams. Well, molar mass is super useful here so that I can get the amount in moles. It's 24.31 grams per mole. So let's go through that process. N is equal to mass over molar mass. As per usual, show your work, show your units. 1.25 grams divided by 24.31 grams per mole. Don't do any sort of rounding, guys. There's going to be lots going on here, so have your full numbers ready to go. 0.051419 ... moles. There we have it. The amount of magnesium. Like I said, this question gets interesting because we also can figure out the amount of hydrochloric acid. We've got the information to do it. We've been given in the question the concentration, which is 0.113 moles per liter. We've been given in the question the volume. Convert it into liters, so divide by 1,000, 0.0800 liters. Be careful with your formulas. When you rearrange this one, it's N equals C times V. So 0.113 moles per liter times 0.0800 liters. Liters are, of course, going to cancel out, and we're going to be left with moles. And this will give us moles of hydrochloric acid. It's a total of 0.00904 moles. All right, here's the common mistake number 1. People compare these two values. You have to use the coefficients to divide by those to actually compare the ratio amounts before you look at which one is limiting. So be careful for that, okay? So for instance, for magnesium, there's a 1 in front. That means I need to take that for magnesium and divide by 1, right? Came from there. Vice versa, for hydrochloric acid, there's a 2 in front. That means I need to take this value and divide by 2, coming from here. Now I'm going to have something I can actually compare. So the balanced chemical equation was step 1. Figuring out the amounts was step 2. Now we're working into step 3 to actually figure out the limiting reagent. This one, of course, is the same, 0.051419 ... moles versus, here we go, This one is going to be, I have to number crunch it, 0.00452 moles. Okay, compare those two values, guys. Which is smaller, 0.05 or 0.004? Well, this one, of course, right? Significantly smaller because it's less. Once we use the coefficients to compare, this is our limiting reagent. That's the one that runs out first. Okay, look at this question. Does it actually ask for the amount of product? Is your goal to find the hydrogen gas or the magnesium chloride? Not at all. The goal of this question is how much excess reagent will remain. Well, if hydrochloric acid is the limiting reagent, that makes magnesium the excess reagent. So we want to know how much ends up not reacting. Here's where things get interesting. Since the hydrochloric acid limits it, then it decides how much magnesium actually reacts. So the way we go about that is still with stoichiometry. We say, okay, let's compare the magnesium solid to the hydrochloric acid it reacts with. And the ratio between those two is 1 to 2, 1 mole to 2 mole. We want to say X, how much magnesium reacts when, now I'm not going to put the 0.04 here. I'm going to go back to the original that actually reacted, right? The 0.009. Okay, so X over 0.00904 moles. Same math we've been doing, cross multiply and divide. We end up with X equal to 1 mole times the 0.00904 moles divided by 2 moles. In the end, X, which is equal to the amount of magnesium reacted, is equal to 0.00452 moles. I'm going to clarify it so I don't get my brain confused. Of magnesium solid reacted. All right, now let's consider this. That's how much reacted. How much is left over? Well, this comes down to how much we started with. Guys, we started with 1.25 grams of this stuff, right? That's how much we began with. So when we converted that 1.25 grams to moles, we got this value, 0.051419. Oh, okay. So if that's what we started with, and this is how much reacted, how do we find out how much is left over? Now we're into simple math again, guys. We just need to subtract these things, right? The total amount of magnesium minus the amount reacted will give us what remains. So in other words, 0.051419 moles minus 0.00452 moles. Number crunch them, we get a total of 0. And now I need my sig digs, which will be 3 of them because of the question. 469 moles of, use the language, excess magnesium solid. Dun, 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 dun. There you have it, guys. Going through with limiting and excess reagents. So it definitely involves an extra bit of thought process and an extra chemical that we need to look at in order to really figure out what is limiting the reaction. Okay, listen to it again if you're not quite clicking. We'll try another one that hopefully will help. So going into another example. Now this one gets very specific. The whole goal of the question is to find the mass of precipitate. And that means we must have a solid forming. And what are we doing? Well, we're reacting a certain volume of a certain concentration of iron 2 sulfate. And then we're given the volume and concentration again, but of a different compound, ammonium phosphate. Look at these two reactants, guys. They're both ionic compounds reacting together. We have a double replacement reaction. So build your equation, FeSO4. Remember, both reactants of double replacement are going to be aqueous. Reacting with my NH4 ammonium, there'll be 3 of those, phosphate, again aqueous. Double replacement, swap out the cations. we're going to end up with Fe3PO4. If you check your solubility table, you will find this is a solid. Ding, ding, ding. That's your precipitate. That's a big deal. And we're going to produce ammonium sulfate, which again, check your solubility table. You'll see that it's aqueous. Balance the whole thing. Of course, we're going to have 3 of the iron 2 sulfates. We'll have 2 ammonium phosphates and produce 3 ammonium sulfates. There you have it. Step 1, balanced chemical equation. Step 2, let's figure out the amounts of both of them to see which one's limiting. So look at what you've been given. Volumes have to be, of course, in liters so that they match the concentrations. So 0.200 liters for the first one. The concentration of that iron 2 sulfate is, oopsies, here we go, equal to 0.118 mole per liter. Pretty simple formula. Number of moles is equal to concentration times volume, right? 0.118 moles per liter times the 0.200 liters, and our number of moles of the iron 2 sulfate is going to be 0.0236 moles. So that just determined our number of moles of iron 2 sulfate. Great. Is it limiting? I don't know. We have no idea yet. We have to do the same process for the ammonium phosphate first. So let's go through it. V equals, divide that 175 mils by 1,000. So we've then converted it into liters, 0.175 liters. Concentration is 0.204 moles per liter. Calculate it. N equals C times V equals 0.204 moles per liter times 0.175 liters. Liters cancel out. Number crunch, number crunch. The number of moles of the ammonium phosphate is 0.0357 moles. Okay, we're at that point again. Do you compare those two numbers? Is that where we find the limiting? This is where you should be saying, no, don't. We need to divide by the coefficients, guys, to figure out the stoichiometric amounts, right? The mole amounts. So for the first one, we're going to divide by 3 because that's the coefficient. For the second one, we're going to divide by 2, the ammonium phosphate, because that's the coefficient. I'm not making up those numbers. That's where they're coming from. So now I need to write out some answers that I can actually compare with each other. We get 0.007866, it keeps on going, moles, versus we get 0.01785 moles. Compare those two, one versus the other. Which one's smaller? That's how we decide. Ding, ding, ding. It is the iron 2 sulfate. There's our limiting reagent. All right, this is the type of question that says, what amount of product do you get? In this case, we want the mass of which one? The precipitate. Well, which one's the precipitate? That's this one because it's the solid formed. So that's going to be our focus. We're comparing the amount of the iron 2 sulfate then to the precipitate formed, the iron 2 phosphate. Why are we using iron 2 sulfate and not the ammonium phosphate? Because the iron 2 sulfate runs out first. It is the limiting reagent. That's our comparison. Now, take a little note. We're going to have to figure out, the whole goal of the question is the mass of this thing. So I always like to get the molar mass then before I keep going. So it's 357.49 grams per mole. That way I already have it ready to go when I need it. Okay, let's compare these ratios. The iron 2 phosphate as compared to the iron 2 sulfate. It is a 1 mole to a 3 mole ratio, as we can see by the coefficients. I'm going to find out how many moles of iron 2 phosphate I have when I react. Now again, here's that common mistake. I'm not using the 0.007866. No, I'm using how much we actually react, which is this one. I just highlighted in purple. That's what needs to go here. Okay, common mistake. So 0.0236 moles. Fine, cross multiply and divide. Let's go through it. X is going to be equal to 1 mole times the 0.0236 moles, divided, of course, by the 3 moles. Number crunch, X is going to be equal to, don't round, 0.00786 ... moles. Last step, let's convert this into mass so that we can answer the question properly. The mass of the precipitate. Rearrange it properly. Mass is equal to N number of moles times molar mass, which is that number I just got, 0.00786 ... moles, times the molar mass, 357.49 grams per mole. And away we go. 3 sig digs is dictated by the question. Mass equals 2.81 grams of Fe3PO4 solid. Dun 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 dun. And there we have it, guys. You've just done 2 limiting reagent and excess reagent questions. Is there a lot to it? Sure, there is a step-by-step, right? Step 1, the balanced reaction. Step 2, figure out the amounts of each reaction. Step 3, find the limiting reagent. Step 4, use the stoichiometric mole ratio to get your answer. But there you have it. Yeah, things are all coming together and there's lots of steps. Like I said, guys, it's an academic course, so think about it. This is significantly less than we would have done in class. For Chem 30, Chem 30 is going to be the full course. Okay, so pick wisely. I'd love to see you all there, but make sure you've been putting the work in so that you can pull it off. Homework wise, you should do in your weekly assignment, please, number 1, 2, and 3 at this point. The good news is there are less podcasts this week. I have 1 more podcast that I'm going to record, and that's going to be it. You'll have that lab that you have to do based upon the video you watch, but yeah, a little bit less listening to me. All right, take care, guys. Talk to you soon.